All right, hello everyone, and welcome to lesson 1.9. Today we're going to be talking about comparing distributions of quantitative variables. You might go, well, wait a minute, haven't we been doing this kind of thing? And the answer is yes. Actually, we've been comparing distributions of quantitative variables for some time, and so this really is a recap and consolidation of a lot of the stuff that we've been doing already. All right. So there's not really a lot of new skills. It's just practicing and applying the things we already know. When we're working on making comparisons of these quantitative variables, we need to remember that any graphical representation or numerical summary can be used to compare two or more independent samples. We could compare things like the means. We could compare things like the standard deviations. We can compare the interquartile ranges of two sets of quantitative data. We can do all kinds of comparisons. As we work through these examples here, you'll notice that sometimes, because these are going to be used on tests, that you'll see some things that kind of lead you in the right direction. But generally speaking, in sort of real-world applications of statistics, you as the statistician are the one who ultimately gets to make those comparisons. So you need to be able to decide which of these kinds of comparisons are the best. Does it make sense to compare the means? Does it make sense to compare the medians? Does it make sense to compare the range and the median? There's all sorts of different ways we can compare things. So we got to work on being flexible and being able to apply each of the different kinds of statistics and read the different kinds of graphical representations that we have seen so far. We're just going to walk through a couple examples. If you want to copy them down, just quick sketches and things. Some of the problems do get a little longer, so the slideshow will be available for you, and you can just go on there and see the problems. The ideas are what's really important, so as you're taking notes, be sure you're writing down the important ideas that I'm sort of going over with how to compare things. All right? So let's imagine this situation. We got two different periods and their test scores on some recent exam. Let's say that Austin claims that second period did better on the test than first period. What could we use to justify or support that claim? So take a look. Think to yourself, what could we use to justify or support the claim that Austin is making that second period did better on the test than first period? Think to yourself. All right. Now, a few things might pop in mind, and I'm just going to sort of talk out loud, and I want you to sort of also take notes on sort of my thinking here. This is a pretty open-ended question. When I look here, I make some observations right away that are probably worth writing down, and then we can turn those things into a conclusion. So in fact, it's actually kind of nice sometimes just to sort of take notes on the side. So let's do that for this problem here. Okay. I noticed that second period, a few things are going on. The median, right, which is that middle line of the box plot, median is greater. It also looks like Q3, actually, it looks like all of them are greater. Let's change that. It looks like the quartile 1, in fact, the minimum, quartile 1, quartile, or the median, sorry, quartile 3 are all greater than first periods. Those same statistics for first period. Interesting. The only one that's not greater is the maximum there. The maximum of first period was greater than the maximum of second period. Okay, so that's an interesting observation here. And in fact, if we want to go like a little above that, it looks like if we take a look at second period, remember each of the sections of the box represents 25% of the data. It looks like the middle 50% of second period's data, middle 50% of second period's test scores are greater than or equal to the 50% to 70%, 50 percentile, 50 percentile, 70 percent, 50 percentile, 70 percent, 50 percentile, 70 percent, 50 percentile, 70 percentile, 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 50 percentile, to 75 percentile scores for period 1. So in other words, this middle half of the box for second period is actually greater than or equal to not just the middle half here, but it's actually greater than or equal to this 50% to 75% range here, which means that this sort of data from second period, the test scores, probably are pretty dramatically higher than first periods. So we have some good sort of observations going on here. I like to just sort of think through those. Even if you don't write them down, just kind of think through those things yourself. Now let's go ahead and write out sort of what our justification might be here. Of these observations we made, what is the strongest or easiest for us to be able to explain? It probably is that first one. I would start by saying the median of second period test scores is greater than the median of first period test scores. Moreover, the minimum value quartile 1 and quartile 1. Oh no, I lost my thing. Wow. What happened? Oh. Okay. Let's try that again. The median of period 2's test scores is greater than the median of period 1's. The minimum quartile 1 and quartile 3 are all for period 2 are all greater than the respective statistics for period 1. That is probably our easiest way into this, simply by comparing the medians here and the fact that the minimum quartile 1 and quartile 3, I can say moreover, like I did earlier before it got deleted, that the respective median of period 2 is greater, and the respective minimum quartile 1 and quartile 3 are all greater. That is probably our easiest way to justify Austin's claim here. Okay, if you want to, you could go in and dig into this other one, that the middle 50% of data for second period is actually greater than or equal to the 50th to the 75th percentile of period 1. Now, it may be worth mentioning that the maximum is not as great, just so that they know you understood that. But in general, it looks like the middle 50% of data, if you want to add that, the middle 50% of data of scores, we should say, of scores for period 2 is greater than that of period 1. Okay, and there we go. Those would be some ways we could justify Austin's claim. And a relatively open-ended question. All right. Let's take a look at some example test questions that have actually appeared before. Now, this one's kind of long. In Northwest Pennsylvania, zoologists recorded the ages and months of 55 bears and whether each bear was male or female. The data are shown in the back-to-back stem plot below. Female, male bear data over here. 7 bar 0 represents 70 months. It's the ages, right? The median age, based on the stem plot, which of the following statements is true? Now, I'm starting to see a few trends here just when I skim. I like to just skim the questions first here. I see that we see median age and range, median and range, median and range, median, range, median, range. Median and range seem to be the thing here. So let me go ahead and find those things for each of these categories here, female and male. So let's find the median here. I want to start at the top here and sort of work my way in. 1, 2, 3, 4. Start at the bottom here. 1, 2, 3, 4. Actually, I guess it's 55 bears total, right? And so we're going to need to go for that. So I went 4 in. I want to go another 4. 1, 2, 3, 4. 1, 2, 3, 4. Make sure you're working the right direction from smallest up and from biggest in. We got to keep going. Another 4. 1, 2, 3, 4. 1, 2, 3, 4 from this side. Looks like we're pretty close. So I need to go 1, 2, 1, 2. It looks like my median over here for females is 42 months. My range would be was 154 minus over here, my smallest one would be 20. So 134 would be my range. I'm just going to write myself a note over there. How about for our males here? All right. The males here, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 1, 2, 1, 1. 22 seems to be the median. Now, you might have been able to eyeball that, and that's okay too. I like to actually just confirm it because sometimes we make bad assumptions when we just eyeball stuff. Our range is going to be 70 minus 15, or 55 months. Now I got my hard data. Let's see. In comparing this, it looks like the median is greater for the females and the range is greater for the females. Is that an option here? The median age and range of both are both greater for female bears than male bears. That seems to be the case here. Let's just hold on to it. The median age and range of are both less for female bears. That's not true. Median and range are greater. The median range is the same. So the median age is the same, but the range, and the range is the same. That's what this guy says. That's not true. They're not the same. The median age is less for female bears than for male bears. That's not true. The median age is greater for female bears. That is true. And the range of ages is less for female bears. No. Median and range are both greater for female bears. And so answer A here. The key takeaway here is don't just eyeball. In this situation, you might have been able to, but that is not going to be the case for all of them. Go ahead, do the work, find the statistic you need. Okay, here's another one. We got what looks like some parallel box plots here. Janelle collected data on the amount of time in minutes each person in a large sample of customers spent in a local store. The data are also included recording the gender of each customer. These data were used to generate the box plots below. Which of the following statements is true? All right. We got these box plots. And again, sometimes it's good just to digest for a second before we go in. Ooh, it looks like that middle 50% of data for females is a lot closer together than the middle 50% of data for males. It also looks like the range is a lot smaller. The low to high for females is a lot smaller than low to high. Look at that outlier up there. This dude spent 90 minutes in this store. Wow. The median of the males is greater as well compared to the females. Okay, so let's see what they're asking. Which of the following statements is true? The range in the amount of time in minutes males in the sample of customers spent in the store is approximately 40 minutes. The range of males is 40 minutes. So that'd be upper minus lower. 90 minus looks like about 5. That is not true. The range for males, I'll do R sub M, is 90 minus 5. That is not going to be true. The mean amount of time in minutes males in the sample of customers spent in the store is approximately 20 minutes. They're asking us about a mean here. Mean would be kind of hard to tell, but based off of this, again, we're given dot plots, and it's skewed to the right. The mean is going to be pulled out farther up here, right? Think about this. We have said that if we have a skewed right data set, the median is at 20, so the mean of a skewed right data set is going to be farther out that direction somewhere, right? So this is not going to be true either. The mean for a skewed right data set is going to be farther out following the skew. So going out to the right to be greater than 20 minutes. The third quartile of the amount of time in minutes males in the sample of customers spent in the store is approximately 45 minutes. The third quartile. So looking over here at the third quartile, that'd be the edge, I'll do a different color, the edge right there of the box. Is it about, what are they saying for us here? 45 minutes? No. 45 minutes, that'd be the fourth quartile. So C is false. Again, see how we're going through each of the work? We're not trying to shy away from doing the actual work here. The interquartile range of the amount of time in minutes in the sample of females spent in the store is 15 minutes. Interquartile range, that'd be Q3 minus Q1, and they're saying it's about 15 minutes. Is that true? Well, if we take a look, it looks like maybe the quartile 1 here is maybe like 8 minutes. Quartile 3 up here is maybe like, what'd that be, 16 minutes? No, it's not going to be 15 minutes. Approximately half of the males in the sample of customers spent at least as much time in the store as any female in this sample of customers. At least half, approximately half, sorry, of the males in the sample spent at least as much time. That is true. If you look at the upper 50%, and I can erase some here, the upper 50% of our male data here, again, the upper 50% starts at that median bar. It's just direction. So 50% of the data lives up here. 50% of our male customers live up here. And so approximately half of the males spent at least as much time, because there's the top of the female category. 50% of the males spent at least as much time as any female in the sample of customers. Because we compare to the maximum there, 50% of males were at least there or bigger. Again, don't eyeball the statistics. Go and find what you need. Again, for these problems, these slides will be available so you can go back and take a look. All right. Of the following dot plots, which represents the set of data with the greatest standard deviation? This is why it's really important to have a good grasp of the different pieces of vocabulary and what they mean. Not just both conceptually and practically. So do you know how to find it, but then also do you know what it means? And this is a good reminder that standard deviation is a measure of typically how close to the mean is the data. All right, and standard deviation goes along with the mean. So if we look in here, it looks like the mean of all of these guys, if we average them, the balancing point will be somewhere right here in the middle. Then we go, okay, which one of these has the highest standard deviation? If standard deviation is going up, that means the observations are farther from the mean. So if we look at each of these sets of data here, which of these little dot plots here is the data most frequently far from the mean? This guy's kind of evenly distributed, so I don't think so. Look at this. This guy's data is all clumped out here and out here. We'll keep an eye on that guy. That's pretty far away from the mean. This guy has some points near the mean, so this one is still going to have the largest standard deviation. D still has some points near the mean, so B is still going to have a larger standard deviation because it doesn't have any points near the mean. And E still has some points near the mean, so it's not going to have a larger standard deviation than over here. Notice here, B then is our answer because the values are farthest away from the mean, or typically farthest away from the mean. The mean's here in the middle, it's a balancing point, but the data's really clumped farther out on the edges, so it has the greatest standard deviation. You can think about standard deviation as how tightly clumped around the mean data is. So if you have some distribution here, if our distribution is actually really tightly clumped around the mean, that would have a really low standard deviation. But if we have stuff that's really far from the mean, that second graph there would have a higher standard deviation. The mean's in the middle, but the data seems to be more clumped farther away from the mean. So you need to know conceptually and practically what your key statistics are. Mean, standard deviation, median, all that stuff. One more here. For the 3 histograms here, which of the following correctly orders the histograms from the one with the smallest proportion of data? So we want the smallest proportion of data above the mean. Mean seems to be key here. To the one with the largest proportion of data above its mean. So we got 3 histograms. Okay, we got one that's skewed to the right. So the mean is going to be pulled out to the right here. Let's go ahead and just mark, maybe the mean's like right there. This one's skewed to the left, so the mean is going to be pulled out, and so maybe the mean's going to be like right there. This guy is roughly symmetric, so the mean is going to be somewhere in the middle with about half the data on either side. All right. So we go, okay, which of these histograms then has the largest or smallest proportion of data above its mean? So we're talking about that direction. All right. So we go, all right, this guy, histogram J, has actually very little data above its mean. So this one I think is going to be the smallest. K has a lot of data clumped above that mean. I think it's going to be biggest. And here the mean kind of splits at 50-50. So, I want to back up, not 2. 3 is going to have the biggest proportion of data above the mean. Notice the towers are bigger there. The bars are bigger compared to over here above the mean. And then our roughly symmetric one seems like it's kind of 50-50 above below the mean. So I think that's going to be our order then. J, L, K. Looks like it's going to be our order here. J, L, K, which will put our answer as B. All right. Cool. So that's just some examples of how to approach these kinds of problems. We really have to hold in our minds all the different things that we have learned and looked at over the course of this unit. All right. A few notes real quick to wrap up. Make sure your comparisons are rooted in observable and quantifiable observations as much as possible. If you're simply asked to compare distributions, do what you can to actually talk about some numbers there. The range is this. The median is this. It is always, always, always better to use hard numbers in your comparisons. As you've seen, also don't back away from the work. If you need to find a mean, find it. If you need to estimate a mean like we did in those histograms, do that. If you need to find a median, do that, okay? Otherwise, you run the risk of making some assumptions that could be dangerous. Also, all the statistics we've learned are fair game. Mean, standard deviation, relative frequencies, medians, interquartile range, outliers, finding outliers using 1.5 times the IQR, or standard deviation plus or minus, mean plus or minus 2 standard deviations. All of those are fair game in these comparisons. They could all be useful tools, so you need to be ready for them. All right. We're going to close out there then and do this. For the rest of this lesson, please complete textbook problems. They're on page 87. They come from the practice test there. Problems T1, which stands for test 1.10 to T1.14. Complete the check-in quiz. That'll be at the end of the self-paced Nearpod. And then I want you also over the weekend to watch and take notes on the normal distribution video that I will post on Google Classroom, okay? It is just designed to give you an introduction to the topic for Monday, because Monday's topic is kind of a big one for us. It's the last new thing, and then we're going to review in the asynchronous homework and take our test on Wednesday. I highly encourage you to do the optional homework. That'll be posted on the weekly grid. And don't forget that I will be posting test review problems and things on the weekly grid and in Google Classroom for you to start reviewing and practicing too, starting this weekend. Also, the con practice is really great. Please make sure you're doing it. You need to have done it in order to get your to earn a retake on the Unit 1 exam. You need to have at least practiced. You don't need to get to like 100%. You need to have practiced each skill that's there. Don't forget, if you turn in an optional homework assignment, every 3 you turn in will count as extra points for your academic habits grades. All right? Take care, everyone.